So from the Newton's laws of motion, you can see previous topic we have already covered the Newton's laws of viscosity topic. So Newton's laws of viscosity is telling about the constitutive law. It is nothing but a telling about the constitutive behavior of the fluid. And what is that fluid behavior? We'll see it here. That is the just like a Hooke's law, is the analogy of the Hooke's law. Hooke's law says that the stress is proportionate to the strain. Here it is telling the shear stress is proportionate to the rate of shear strain rate. Shear strain rate. Rate is concerned here because fluid undergoes for the continuous deformation from the definition we have already seen, and shear stress. And it is a linear relationship. It's a linear relationship. So stress is a function of strain rate, and it's a linear relationship. From the material property it is coming. If you proportionate, if you equality, if you go some proportionate constant into this. This constant and is coming from the material behavior. Material behavior. And this mu is known as the dynamic viscosity. We got that unit, SI unit, we are getting it, Newton per meter square, or we can say it Pascal second, or we can be able to say kg per meter second. CGS unit is the name of poise is called the. This thing we have seen it. Now the topic is the kinematic viscosity. Kinematic viscosity is defined. You see the most interesting case here, kinematic viscosity. We are telling it by the mu is nothing but the dynamic viscosity divided by density. Both we are knowing about dynamic viscosity, the proportionality constant it is coming by density. So what is dynamic viscosity is telling? Actually, dynamic viscosity is giving you the idea that diffusion of the momentum disturbance. So, because viscosity is the messenger, we have already told the viscosity is the messenger for momentum disturbance. If there is any momentum disturbance is there, it is convey the momentum disturbance. It is sending the momentum disturbance. The viscosity is sending the momentum disturbance. The messenger of momentum disturbance. Diffuse the momentum disturbance, better to say. Whereas the density term is trying to keep the momentum. Density trying to keep momentum. So whenever we're dividing this mu by, so it becomes a relative indicator. Which is telling about the how fast momentum disturbance can be conveyed from one layer to other layer. How fast or slow. This can be, if I want to know this thing, this can be known from the kinematic viscosity. So kinematic viscosity is a relative indicator. The indicator of the fluid, how fast it is conveyed its momentum. So because the momentum disturbance conveyed by the dynamic viscosity, whereas with respect to the keeping the momentum, So kinematic viscosity is a relative indicator of the fluid property. That to convey or diffuse the momentum disturbance with respect to the maintaining the momentum disturbance. This concept is coming. How fast or how slow it is conveying the momentum disturbance. Definitely viscosity, mu is conveying the momentum disturbance. But how fast? So that can be determined by mu by rho or mu. So what should be the unit? If we go the unit, so SI unit. So mu SI unit. So if you write it down, the mu SI unit kg per meter second. What does it by the rho? Rho is kg per meter cube. So it will comes meter square per second. CGS unit similar way, semi-square. So area per second. How much area it will cover per second? Better to say. How much area it will cover per second? And if there is a point disturbance, with the time, how much area it can be covered in this way? If it is more, so fast momentum disturbance is propagating one place to other place. That is the concept here. So semi-square second, it can be say as the Stokes. The CGS unit, semi-square per second, is known as the Stokes. So conversion, 1 meter square per second is equal to 10 to the power 4 semi-square per second. That is the only conversion. Sometimes we are talking about the centistokes also. Centistokes. So 1 centistokes means you have to. So 1 centistokes divided by 2 again. So we are not doing that so many conversion, just is telling like this. So the viscosity, dynamic viscosity. So dynamic viscosity unit, we are talking about SI unit, Newton second per meter square. CGS unit, poise. One more unit is there, we're telling you, that is FPS unit is Reynolds. FPS unit is Reynolds. So you can write it down, the poundal force. Because of the Newton, you can convert the poundal force. Poundal force, 1 pound, poundal force, divided by the inch square. Same one. 1 force pound. 1 pound into 9.81, the poundal force. Here it is known as the Reynolds. So we are not going to the FPS unit just for getting, because the Reynolds is keeping the concept of the viscosity. Is also the Reynolds number, which is determined. We'll see better one by one thing. Now the most important thing, what is the cause of the viscosity? Basically, the 2 main causes there for the viscosity. One is the molecular, intermolecular attraction force. Molecular attraction force or intermolecular. 2 molecules attraction force, or it is known as the cohesion. Intermolecular attraction force. Another reason is the molecular momentum transfer. Molecular momentum transfer. In case of the liquid, if you consider in case of the liquid, the molecular attraction force is dominating. This quantity is dominating for the liquid. So viscosity of the liquid is mostly depends on the intermolecular attraction force. Whereas the gas, in between two molecules, attraction force is very less. So here, the molecular momentum transfer comes into the picture. So molecular momentum transfer is dominating in case of the gas. The viscosity of the liquid depends on the intermolecular attraction force. The viscosity of the gas depends on the molecular momentum transfer. This is the cause. Now, if you increase the temperature, what is the relationship of the viscosity with the temperature? If you increase the temperature, the attraction force, intermolecular attraction force is decreasing. If you increase the temperature, intermolecular attraction force is decreasing. Because of the temperature, it will goes apart. Volume will be increased. So between two molecules, the attraction force will be decreased. Hence, the viscosity of the liquid will also decrease, because liquid viscosity mostly depends on the intermolecular attraction force. Liquid in case of the liquid, the viscosity depends on the intermolecular attraction force. I am talking about the both viscosity here, whether the viscosity is the dynamic or the viscosity is the kinematic. Both cases, it will decrease for the liquid. If you increase the temperature, the viscosity of the liquid will definitely decrease. Both. But in case of the gas, it is very interesting thing. In case of the gas, if you increase the temperature, your viscosity, mu is increasing, as well as the nu is also. Kinematic, dynamic, and kinematic both will increase. The opposite phenomenon. Here, the temperature, if you increase, for the case of the liquid, mu decrease, nu decrease. That is the case of the liquid. For the case of the gas, if you increase temperature, mu also increase, nu also increase, because the momentum transfer is, intermolecular momentum transfer is increasing with the temperature. Because it is causing the thermal random motion. It will cause the random motion here. How it is a random motion? We are talking about, let us see the gas molecules. Two layers of gas molecules, considering here. This layer is the U plus del U. This layer is the two layers of gas molecules. Now, if you increase the temperature of the gas, so the molecules will get some thermal motion, random thermal motion in this direction. All molecules is getting some random thermal motion. Because of the temperature increase, it will get some random thermal motion. I'm talking about the gas, not liquid here. So what will be happen? Let you take here, N is the number density of gas. That means per unit volume, N number of molecules is present. So N number of molecules per unit volume. Now, as you increase the temperature T, these molecules will get some velocity due to the thermal motion. Due to the random thermal motion, the molecules will get some velocity, and that is nothing but alpha into PTH. Alpha is the correction factor into PTH. PTH from the kinetic theory of gas From the kinetic theory of gas, you will get the VTH is root over 8 RT by pi. You will get some velocity. These molecules will get some velocity. So it is getting velocity in this y direction. So along y direction, so displacement, swift displacement, how much shifting displacement will be occurred? Velocity into delta t, time. Let the time is the delta t time. So velocity into displacement. So alpha delta t. Velocity is this one. That is the displacement. How much volume? Swift volume. This is the displacement into area. Delta area. Let you take the area, delta A. Cross-sectional area, delta A. So how many molecules will be taking part in this thermal motion? That is the volume. So how many molecules, number of molecules taking part in this interaction, thermal interaction? N into volume. N is the number density into the volume. Each molecule, what is the mass? Let you take the each molecule mass is smaller. Each molecule's mass is small m, so this. So mass of the molecules. What is the momentum of the molecules? Of the same molecules, momentum. This mass into velocity changes. Change in momentum. Change in momentum here. This mass into momentum. Mass of the molecules. That is the mass of the molecules. Whatever we are writing till now. Mass of the molecules into change in momentum. Rate of change of momentum flux. Rate of change in momentum flux. Flux means you have to divide it by the area, and rate means you have to divide it by the delta t. So this total term, if you divide it by delta t and delta a, this will be cancelled out. What would be the remaining? M n alpha 8 RT by pi into del U. Rate of change in momentum flux. Rate of change of momentum is the force. Flux. Force flux means force by area. So tau. Here only the shear component is acting. The force by area is the tau. So that is nothing but the tau. Force, rate of change of momentum, force divided by the area flux, force flux. Shear. From Newton's laws of viscosity, we know tau is equal to mu du dy. Partial differentiation we are writing. It may be, u may be depends on the x and y, that's why we are not going that much detail. Now, kinematics of the fluid, we will see this. What about the del mu? Del mu, you can write it in the partial differentiation form into. So del u, you can write it the change of velocity del u by del y into lambda. Lambda is, we are mentioning here, the lambda is nothing but what do we know by the lambda? Lambda here, the in between two collision, how much distance traveled by the molecules. free path of molecules or molecular free path. That is the lambda. That is molecular free path. In between two collision, how much statistically, how much distance a molecule can be traveled is known as the lambda. So from this equation, from this here, if you get it, from this case, if you get this equation in this way, writing here, if you compare this equation with it, if you compare this equation with it, you will get tau is equal to mu du dy is equal to m n alpha 8 RT by lambda du by dy. So hence, you are getting here mu is equal to the only things we are writing here. So we can write it mu is equal to m into n into alpha into lambda into 8 RT by pi. M is the mass of each molecule, n is the number of molecules per volume. So Mn is the mass of molecules per unit volume, that means rho density, into alpha correction factor, into molecular free path, into 8 RT. We are considering it is for the ideal gas, this equation for the ideal gas. So if you increase T here, temperature, your viscosity will be increased for the gas. That is talking about. We are talking about this thing. If you increase the temperature, your mu will be increased. That's all here. We are not going that much far. So mu, we are getting in this way. One concept